So what I'm going to talk about is one of the things that Ramanujan is quite famous for, namely this discovery of the Mach theta functions. And one of the mysteries in thinking about this is why in the world would he have thought this up? It's going to be necessary in this talk to, so to speak, get down in the weeds. And generally, talks for a general audience down in the weeds, I have leave something to be desired. But I do think this is a significant question, and it will be hard to communicate how he did this without really getting our hands dirty. At least I hope at the beginning to do some prototype examples so that you can basically get a feeling for how this might have happened. Also, I have to apologize. As I looked through my slides this morning, I realized that there are a number of typos, and the first typo appears on the second slide. This is not from, well, it is from page 127 of the published version of Ramanujan's Lost Notebook, but it gives the title gives the impression that it is from his Lost Notebook. It's actually part of the last letter that he sent to G.H. Hardy in 1920. Since I have such a large Indian audience, I won't tell you the story of Ramanujan's life, just to remind you that he, as an Indian without many financial resources, was befriended by G.H. Hardy. He went to England in 1914, worked on numerous projects with Hardy, writing really papers that had tremendous influence on the research in number theory and related topics through the 20th century. He got ill and unfortunately convalesced in England, and it was thought his health might improve if he returned to India, which he did in 1919. Unfortunately, his health got worse and he died in April of 1920. In January of 1920, he wrote a letter to Hardy, and this letter, says Hardy noted, said nothing about his health, but only talked about what he said were some very interesting functions recently, which I call Mach theta functions. Now, depending on the resolution of your computer, you may or may not be able to make out much of anything on this page. So let me write it out in a form that is somewhat easier to read. At the top of the page, it starts, if we consider a theta function in transformed Eulerian form, and by Eulerian form, he means what we now call Q series or basic hypergeometric series, where you have these rising Q factorials, 1 minus Q, 1 minus Q squared, 1 minus Q cubed, etc. And he focuses on two of these series. The first one turns out to be the series that Jacobi actually needed in order to prove Jacobi's triple product. The second one is the series from the first Rogers-Ramanujan identity. Ramanujan notes that it is possible to determine the nature of the singularities at the points, and here, in other words, at the roots of unity on the unit circle. Please forgive my cuckoo clock that is cuckooing in the background. These are the points on the unit circle, and he remarks that we know how beautifully the asymptotic form of these functions can be expressed in very neat closed exponential form. And the reason for that is if you rewrite A and B succinctly, as I've done here, where the notation is the class standard Q notation for these finite Q Pochhammer symbols, then the first series A, namely the thing that you see at the top of the screen there, and B, which I have written out more extensively here, the A is equal to the generating function for P of n, the number of partitions of n. It's effectively the modulo a multiplier. It's the reciprocal of the Theta function. It's a modular form. B On the right-hand side, you have another, in fact, a modular function, again, transforming under a different modular group, but nonetheless, the nifty asymptotics that Ramanujan describes in his letter that are given in the middle of the page, and which is what he is most concentrating on as what's nifty about theta functions. The asymptotics there are all produced by the representation on the right-hand side. One can get some asymptotics for the behavior utilizing things like the saddle point method, looking at the left-hand side, but the right-hand side is where you get this truly amazing clarity of the exponential nature of the singularity. Ramanujan then proceeds to speculate about the possibility of the functions that, one, behave beautifully near the unit circle, and two, are not theta functions, or as we might say, modular forms. While Ramanujan says he has not proved the existence of such functions, he nonetheless lists 17 functions which he firmly believes are these new functions, which he terms Mach theta functions. So now I've come to my second typo of the morning. The top line, every minus sign you see in the line defining F3 of Q should be a plus sign. So this series should read 1 plus Q over 1 plus Q quantity squared, and then 1 plus Q squared, 1 plus Q squared. All the minus signs in the top row should be a plus. Otherwise, everything is correct here. So Ramanujan lists these three functions in his letter to Hardy, and he makes the following assertions about them. And the thing that you should have noted for you is that these linear combinations that he has made up are equal to, if you look at the bottom of the screen, equal to a classical theta function, theta 4, times a classical infinite product, which is basically an eta quotient, so that the right-hand side is a modular form, whereas he's asserting that while the F, phi, and psi are not modular forms, these linear combinations produce modular forms. But what would have given Ramanujan the idea that such functions might be possible? In addition, why latch on to these three? I mean, of course, if you look at the three of them, they look very much like A and B. And so you say, well, okay, fine. But the behavior of these functions is very rare. If you write down, Ramanujan gives an example of one that looks like all of these, where the behavior near the unit circle is not nice at all. And it would be a true statement that if you sort of write down such a series randomly, the probability is close to 100% that you're going to have some function that is not either in Ramanujan's notation, a classical theta function or a Mach theta function. So this is the main topic of the talk this morning, what would have given him the idea. So I believe that Ramanujan's study of identities like the Heine transformation, which I do not believe knew it was the Heine transformation. He undoubtedly had it, although it's not in full generality in his writings. There are enough special cases of it that one would believe that he had it. And I believe that this sort of thing led him to discover the Mach theta functions. So in order to understand what I'm getting at, I'm going to actually give you a proof of this transformation due to Heine back in the middle of the 19th century. And it relies on a very much simpler formula, namely what is called the Q binomial series. And it is the assertion that this infinite series equals the infinite product here. And he uses that series, and he uses a way of writing, and here's a next typo. The capital N on the bottom line should be a little n. He rewrites these finite products as taking the full infinite product and then canceling out every term starting with the nth term and beyond, so that you write a finite product as a quotient of two infinite products. This seems at first glance to be somewhat counterintuitive. It seems like you're not reducing entropy, but increasing it. But surprisingly, this works extremely well. So let's see how the proof goes. So here's, as you see, is the left-hand side. And what have I done? I've taken the B product and the C product and rewritten them as the quotient of two infinite products. Of course, the part of the one infinite product that does not involve the index n, it can then be factored out. And so we're left with a series that looks like this. So this is the crucial idea. What you do now is to look at this infinite product right here and utilize the Q binomial series in order to expand it into an infinite series. And so this is precisely what is done in the next line. And then you interchange the order of summation. Of course, we need conditions in order to guarantee the absolute convergence of all the series involved so that this is legitimate. All those conditions are easily supplied, but they will distract from the flow of the argument, which is what I want to emphasize. So all that's happened in the third line is the exchange of the order of summation. But the exchange of order of summation produces another instance on the interior. The n sum is now another instance of the Q binomial series, so that you can sum it now into an infinite product by using the Q binomial series formula to make that infinite series into an infinite product. And now you see you have one of the infinite products related to the expression that you see at the bottom of the screen here. And so you may now factor it out and put in its place another infinite product and a finite product. And what you have at the bottom of the screen is precisely Heine's transformation. So this is the full proof, and the mechanism that you have seen here in how one proceeded from the upper left-hand series to the expression at the bottom of the screen. This is something that clearly Ramanujan was not only familiar with, but able to execute in circumstances that are somewhat more challenging than Heine's transformation. But at least the one message I want to get over, that what I believe to be true is, it is Ramanujan's facility in dealing with identities of this nature that led him to the Mach theta functions. There is much more that is possible with this method, as Ramanujan clearly reveals in the Lost Notebook. For example, I write down here one such formula, and it again is proved in exactly the way that I proved this before. Oh, and here is a further example. Both of these, say, appear on page 3 of Ramanujan's Lost Notebook. The first one is right at the bottom of the screen. Part of your reason for not seeing this too clearly is there's a lot packed onto each page. Also, Ramanujan seldom wrote with the modern capital sigma notation. He generally wrote down 3 terms of an infinite series. And since no exponent was worse than quadratic, 3 terms of an infinite series completely determined the infinite series. And so you were able to see these formulas. But here, for example, are 2 examples, each proved in that way. Here are 2 or 3 more. Again, each of them is proved in exactly the same way, just utilizing the binomial series and this way of changing finite products into a quotient of infinite products. There's a certain surprise with respect to the last formula here, in that all of a sudden you have two series on the right. How in the world did that happen? So I'm going to take the last series, this series that you see on the left. I'm not going to go through the entire proof of this, but I am going to indicate how that happens, because that sort of thing, I need you to see how this can arise, how this can bifurcate into two series, because this is what happens in what I suggest is Ramanujan's discovery voyage for the Mach theta functions. So to start with, we take the series on the left and we change this finite product in the numerator, AQ, Q sub n, into a quotient of two infinite products. And now we use the Q binomial series in the limiting case, where the top parameter is 0. We use it to determine an infinite series for the infinite product, a q to the n plus 1 q. And we proceed from there to now interchange the order of summation. The series on n is now a further instance of the Q binomial series. However, it's a limiting case so that you actually get this quadratic exponent in the numerator. The formula that we're using to sum it actually goes back to Euler. So Euler had two instances of the Q binomial series. And what this series on the end sums to is the infinite product that you see here. Now, this product is going to be an infinite product of the form 1 plus q to an integer power, but it will depend on whether if m is even, all the powers on m in the product will be odd, and if m is odd, all the powers in the product will be even. So it will have a dramatic effect on what the product is like, whether m is odd or even. And consequently, what you do is to separate it into two parts according to m even in the first case or m odd in the second. And now you're able to proceed in the way that one saw before. It is now possible. I won't carry you through the rest of the proof, but what I wanted to show you is that the effect right here at the bottom of the screen forces one to look at two series rather than one because of the different behavior produced by the exponent being odd or even. So we'll now return to series A. Okay, let us recall series A because that is right after the introductory sentence. That's the first thing that Ramanujan looked at, is this infinite series. And I suggest to you that one of the things that might have intrigued Ramanujan would be, could I operate with the Heine method on this infinite series? And the answer, at least as it stands now, is no. Because if we want to apply a Heine type transformation to this with q to the n squared in the numerator, we need q squared sub n in the denominator. If we had a q squared instead of the square on the outside of this product, if the squares were on the q's on the inside, then we could proceed. But we don't have that. Well, Ramanujan, not to be deterred, I suggest, said, why don't I rig it? So I will put that product there, and then I will cancel out factors in order to make this an identity. And so the only thing going on here is the old algebra idea that 1 minus x squared is 1 minus x times 1 plus x. And so 1 minus q to the 2j is 1 minus q to the j times 1 plus q to the j. And so Ramanujan cancels out the plus factors with this numerator product. And so now, changing the original A series into this form, Ramanujan, with his incredible curiosity, is going to proceed to see what happens. So he does, if my So everything I'm saying here is conjecture. So if I say Ramanujan thought this, what I'm really saying is I'm guessing Ramanujan thought this. But what happens here then is the procedure just like we did in Heine's theorem, namely, you replace these two finite products by a quotient. Each one of them is a quotient of two infinite products, so that the series now becomes this. All right. Now you have right inside here something that is amenable to the Q binomial series. All right. So that's what you get for the Q binomial series. And now, what do you do? Everything from here on is almost algorithmic, not quite, but almost. You interchange the order of summation and you sum the end sum. And the end sum is, again, by limiting case of the Q binomial series, it's this infinite product. Well, the reason I chose the other example from, well, there are a couple of reasons I chose the other example from the Lost Notebook, but one reason I chose it was to show you that in order to proceed with something like this, you have to bifurcate the series according to whether M is even or odd. So what we obtain now by taking M first even and M odd is the two expressions that you see here multiplied by the infinite products out front. So our original series that Ramanujan was so emphasizing in his letter on the Mach theta functions, this series has now been deformed into what you see here. Now, one might feel that things are not going well because you have gone from a very simple series to a mixture of two rather complicated infinite series and infinite products. But there are still many possibilities. So although we have not seen much entropy reduction here, nonetheless, we can perform the same operation of reversing things that we saw in the Heine transformation. And consequently, we can rewrite the two infinite series in the manner that you see here, getting all the infinite products outside of the series. And what remains in the series are finite products. But what is particularly neat is that cancellation has occurred. In other words, the infinite product that you see here, when it's pulled out, part of it glues on to the finite product in here to give this infinite product, leaving this remainder of what is there, and the denominator stays just as it is. So this is different from what happened in Heine's transformation, and obviously Ramanujan was watching out for it and took advantage of it. And similarly, in the second line, this pulls out from these factors the even parts and leaves him with this. And where does this go from here? Well, the reason that I rewrite things in the form that you see down here is because I put a zero, put a phantom finite product in the numerator of the two series above, and I've split the denominator factors into two parts on modulus q squared. In other words, I split the exponents that are even from the exponents that are odd in each of these series. And the reason I do that is to show that what I have on the screen is two instances of the Heine series itself. The base is not Q any longer, it's Q squared, but both of these are Heine series. And so we can apply Heine's transformation to them. So that would take several more slides. And I'm hoping that I can end the talk a little early because I recognize that many of you are fighting sleep, I hope successfully. And so I want to sort of hit the highlights of what's going on. So we've already seen Heine's transformation. Each of the two final series is a series of this form. Once you apply Heine and do a variety of simplifications, the whole thing boils down to this, namely the left-hand side. Remember, the left-hand side is just that we see there, which is, if you recall my initial slides, I don't want to go back through all of those, initial slides, this is 1 over QQ infinity. It's the generating function for P of n. And so what you have are a bunch of infinite products. All the infinite products, incidentally, are modular forms. And you have these two series. So let me summarize everything. There is a famous identity, I believe, going back to Gauss, but maybe Jacobi. I'm not sure which, and never have been sure which. Anyway, this is the theta 4 series. And if you use it to simplify the expressions here, this is what you obtain. And I won't go back to the original slide, but I will tell you that this is this is the phi Mach theta function. This is the psi Mach theta function. The threes have been introduced in the printed version, the edited version of the Lost Notebook that Bruce Baird and I collaborated on, which takes 5 volumes. We put 3 on these to designate that they're the third order Mach theta functions. But what you obtain is this really strikingly simple identity, even though the proof that we went through started out from this formula for 1 over QQ infinity, and you simplifies to that. I claim that this is the aha moment. This is, I believe that when Ramanujan saw this formula that we see in the middle of the screen here, his eyes would have lit up, because these series do not behave in any sort of uniform manner at all the roots of unity on the unit circle, namely where certain roots of unity, they head to some value other than one that will make the denominator singular, make the expression singular, so that although each of these roots of unity is an essential singularity for these functions, the radial approach to them does not tend to infinity. At certain roots of unity, phi 3 of minus q remains bounded as q tends to rho. At others, it has to behave exactly like the left-hand side, because when one of them is remaining finite as q radially approaches that value on the boundary, the other one has to then behave asymptotically precisely like this, because the difference between the two of them is bounded. Now, it's not difficult to show that the limits are, the bounded limits are easily proved. I'm just going to take the simplest example, namely the phi 3 of minus q as q tends to 1 from the left. I claim this is equal to minus 1. And the sort of proof I'm giving is easily adapted to deal with any of the other cases. Namely, you split the series into 2 parts, n equal 1 to capital N, and then capital N plus 1 to infinity. And from n goes from 1 to capital N, as q tends to 1 from the left, each term in the series becomes minus 1 to the n over 2 to the n. And it's the finite geometric series which sums to the expression you see there. The second term, you can easily show that the terms are bounded. And here's another typo, bounded by 2 raised to the nth power. Sorry about that. And consequently, the tail of the series tends to zero as capital N tends to infinity, and the limit is easily proved. So that, I believe, is the, so to speak, aha moment. Now, given Ramanujan's fertile imagination and appreciation of the things that might be possible, he would so the things we've dealt with really are this Mach theta functions phi and psi, which you'll notice that he lists first. He lists first after discussion of this function f, but f is, wait a minute. So F3 is this series. So as you recall, I had some errors before, but now this is correct, where you have this series. Instead of QQ sub n, you have minus QQ sub n. And you can go through exactly the same argument that I went through with the original series, and you'll wind up with this. And from this, the relevant identities follow. The relevant identities are the ones I've showed you, are the ones right in the middle of this slide. But Ramanujan does not stop here, and I believe that, excuse me. Ramanujan does not stop here, and I believe that the methods that intrigued him with series B, which was the first identity in the Rogers-Ramanujan identities. And here are 4 more Mach theta functions. Actually, there are 5 of them. And there's the 5th one. And there is a second family of 5th order Mach theta functions that he lists on this screen. Let me suggest to you where those came from. So consider an identity from the lost notebook that we sketched the proof of it earlier. We didn't carry it out in full. But what happens when you set A equal minus 1 in this? When you set equal minus 1, the series on the left becomes the series in the Rogers-Ramanujan identities. And when you set A equal 1, it becomes Ramanujan's f of q right here, the first of the 5th order Mach theta functions. Actually, it's this f of q. And the next one, of course, is related to the second Rogers-Ramanujan identity. And these sorts of identities that you see here with A equal minus 1 and A equal 1 are producing the identities from which you can deduce the things that Ramanujan sent to Hardy. So this, not only does this argument set up show you the aha moment, show you the reason that you would think these series are significant, but would lead you to, I believe, all of the formulas that Ramanujan found. The behavior, the reason that you get this wonderful Mach theta function behavior is precisely because of this behavior near the unit circle. And so once he saw that, then he realized that if these functions weren't some sort of modular form, they behaved in really this radical way of, and in fact, half the time they're behaving exactly like a modular form, and the other half the time they are bounded as they approach the unit circle. And it seems to me very likely that this is the case. So in the last letter to Hardy, and these are the last 2 pages of the last letter to Hardy, and indeed they were published, Hardy published them in the collected papers of Ramanujan, so everybody had a chance to see them from the mid-20s onward. Besides these functions here, from there at the bottom of the slide, it says Mach theta functions of 7th order, and he lists 3 more series, and the last words, which are not shown here but are written at the bottom of the letter, is these 3 functions are not related to each other. And so you have 0 indication of why he thought they were 7th order functions. So I've shown you this set of things. I ask about what can one say about the 7th order functions? And the answer is, so far as what Ramanujan has, it is a giant question mark. I should say a little more about the 5th order functions. Watson, using a much more, so to speak, intricate technique, was able to determine the behavior of these 3rd order functions near the unit circle. His paper in 1937, The Final Problem, an account of the Mach theta functions, well explains this, but it uses things that do not apply at all to the 5th order functions. And consequently, Watson, in a second paper on the 5th order functions, proves all the identities that Ramanujan has, but states that it looked to him like he was very leery of the full definition of Mach theta function here, because he could not find formulas as he found for the 3rd order functions that would allow him to make the same sort of asymptotic observations, not close to the asymptotic observations that Ramanujan was really requiring in order to call something a Mach theta function. So one of the most exciting things about discovering the lost notebook was to find in the lost notebook all of these functions, so that it was clear that when Ramanujan wrote the pages that make up the lost notebook, namely right when in the last year of his life, and he has all the neat formulas that Watson found for the 3rd order functions that allowed Watson to prove their behavior near the unit circle. In addition, he has formulas that will allow one to prove the behavior of the 5th order functions near the unit circle. In other words, he has formulas that Watson conjectured did not exist. So he had tremendous insight here. We have no idea how he came up with these formulas. He had to have some sort of understanding of things way beyond what he wrote down, because it is not clear from what he wrote down why he would think that these things were Mach theta functions, yet he is absolutely 100% convinced of their behavior. And it should be pointed out that the discoveries of the last part of the 20th century and now into the 21st century have not only shown that all of these functions, not only the 5th order ones and the 3rd order, but also the 7th order, have exactly this behavior. Ken Ono and his colleagues have done immense amounts in connecting the Mach theta functions with weak harmonic weak Moss forms. Zonders-Vegers is probably the pioneer in making these sorts of observations. And so there's been an explosion of applications of the Mach theta functions. But it's always seemed to me to have been an important question of where did these come from, and hopefully points to the fact that Ramanujan may well have been onto something in looking at these functions in terms of these Eulerian or basic series, and there is really lots more to be done into fully understanding that aspect of Mach theta functions. And with that, I thank you very much for your attention. I realize that it's late, and so I think I'm 10 minutes early in ending. I would be happy to answer any questions for all of you who are still awake.
Okay, thank you, Professor Andrews, for this nice talk.